Yes, sir.
All right. So please pay attention on the screen now, right? So in the previous class, we have seen the isoparametric element, subparametric element, and the superparametric element. So this is just a concept. This can be used for 1D problem, 2D problem, as well as for the 3D problem. Okay. This particular thing we have learned in the Cartesian coordinate system as well as in the natural coordinate system now. So we will continue with the natural coordinate system, and today we are going to see the derivation of a triangular element using the Cartesian coordinates, so using the natural coordinate system. Okay, so now let me draw a simple rectangle over here. Okay, sorry, triangle over here. So here you see this side I have x-axis. Okay, so earlier we have two different things, right? One is in the Cartesian coordinate system and second one is in the natural coordinate system. Okay, so let us say on the left hand side we have a Cartesian coordinate system where you have a triangular element which is like this. Okay, but in the natural coordinate system we are considering the element like this. Okay, why we are considering this is because we know that the element is spread over the distance of only 1 units. Okay, so here let me draw some connectivity also. So here I have this is node number 1. Okay, this is node number 2, and this will be your node number 3. Okay, so that this side we have x-axis and this side we have y-axis. Correspondingly, now you will have some coordinates like x1 y1. Here you will have something like x2 and y2, and here you will have x3 and y3. Okay, now in the natural coordinate system, what we are assuming that this direction is your xi. Okay, so xi is very much similar to your x-axis, and here we have a eta axis. Okay, so in place of y now we have a eta axis, and this element also has got three nodes. Okay, so this will be one node, this will be another node, and this will be also another node over here. Okay, now what we are assuming this over here, this will be your node number 1, this will be your node number 2, and third node will be at the origin. Right now, if you remember, we have considered the distances in the natural coordinate system. It is in the range of -1 to +1, right? So maximum is +1 and minimum is -1. So since we have assumed the nodal coordinates or the shape of the triangle like this, so if you consider this, so here the value of x and y, or rather I should say xi and eta, they will be 0 0, and here you will be having the x coordinate as 1 and y coordinate as 0, because this is the maximum limit. Okay, and as far as this part is concerned, its x coordinate will be 0 and y coordinate will be 1. Okay, is it understood to everybody? Are there any queries as far as this part is concerned? This is just an assumption. सबको समझ में आया why we have taken one this side and one that side? Yes, समझ में आया?
Sir,
Yes, बोलो.
sir, both the triangles we have assumed are not same.
They are not same. Exactly.
Sir, can you please explain both the triangles, the Cartesian system and
See, in the Cartesian system, what happens? We are working in a real life scenario where every node has got a different x and y. Okay, so x value can be 10, x value can be 5, it can be any value. Okay, because it is depending on your axis. But in the case of natural coordinate system, it is having a coordinate system which is related to that particular element only. Okay, now in the natural coordinate system, if you remember the bar element, we have used the upper limit and lower limit as 1 and -1. So the spread of that particular element is only from -1 to +1. Okay, so it is having the spread in the direction of xi. Okay, we are not talking about x and y. Okay, because those two are different coordinate system. Okay, so the Cartesian coordinate system will be a real life coordinate system where whenever you are going to solve a problem, you will be getting the nodal coordinates in the Cartesian coordinate only. Okay, but in the natural coordinates it will be always in terms of 1 and 0, and with the help of this 1 and 0, now we are going to derive this. Okay, so two things are different. We have already defined, or we have already derived the stiffness matrix using the Cartesian coordinate system. Now we are going for the natural coordinate system. Okay, I hope this is clear to everybody.
Yes, sir.
Okay, Saurabh?
Yes, sir.
Okay, so now let us focus on that. So if you remember, when we have used a derivation of CST, at that particular point we have assumed this deformation at node 1 in the horizontal direction as u1, and here we have used this as v1. Okay, whereas here this is u2 and here this is v2. Here this will be, let us say, u3, and this will be, let us say, v3. Okay, now when I talk about the natural coordinate system, in that particular case every node will be having a deformation, and if you remember, we are using the nodal deformation in the natural coordinate system with the symbol q. So what I am going to do over here is, on this side, okay, in the z-axis, I am going to assume this as your q1. Okay, so the q1 is nothing but the deformation at node 1 along the z-axis. The same I'm assuming this over here as q2, and over here this as q3. Okay, and in the vertical side I'm assuming this as q4, and on this side I'm assuming this as q5. Okay, and I'm assuming this as q6. Okay, both are same, but the coordinate system is completely different. Okay, so now let us try and let us go for a derivation of this particular uh, stiffness matrix for this particular element. Okay, so now you see, you are solving a two-dimensional problem where the geometry is defined in x direction as well as in the y direction. So if you remember, we have used a displacement polynomial for Cartesian coordinate system, as it was something like x is equal to a1 plus a2 times say I think we have used u, not x. Okay, I think we have used u. Okay, so we have used u was depending on x as well as y. Okay, and we have also seen v is depending on, let us say, a4 plus a5 times x and plus a6 times y. This is what we have done in the Cartesian coordinate system. Okay, but in the natural coordinate system everything has to be defined in terms of xi and eta. Okay, so first of all you need to correlate the x with, say, xi. Okay, so this we have done in 1D, and we also have to correlate y with now eta. Okay, so because whenever you will be solving a problem, you will be getting like this. Okay, and we are right now going for derivation for this part. Okay, so first of all we need to establish the relationship between x and xi. We also need to establish the relationship of u and v with this q. Okay, so I have written q1, q2, q3, q4, q5 and q6. So they are nothing but the deformation or the nodal deformations u and v in the Cartesian coordinate system. Okay, so how to do this? So for this purpose we have to assume the displacement polynomial. So let us assume displacement polynomial of x is equal to a1 plus a2 times xi plus a3 times eta. Okay, remember in the previous class when we are going for 1D problem, we have used x is equal to a1 plus a2 times xi. We have used only this one, isn't it? And when we have used three noded bar element, in that case we have also added something like a3 times xi square. There was no eta term. Okay, but since this is a 2D problem, so your x is also depending on eta. That's why we are using this particular expression over here. Okay, so now with this, now what we can do is we have to go for the derivation. At the same time we can also use a similar kind of displacement polynomial to define the relationship between y and uh, y with xi and eta. So here I can say this will be something like a4, okay, plus a5 times xi plus a6 times eta. So I am writing now two different a displacement polynomial. This is based on my assumption. So now what we have to do is we have to first of all find out what are these unknown constants. Okay, so for the time being, you just forget about this y. Okay, you just forget about this y. Let us focus on this x only. Okay, so what I can do is I can apply the boundary conditions over here. So I can say at node 1, so let me write down over here. So at node 1, okay, so at node 1, x is nothing but your x1, isn't it? Your xi, okay, so xi value, if you see in this particular figure, so xi value at node 1, so your node 1 is basically over here. Okay, this is your node 1. So the xi value at node 1 is nothing but your 1, isn't it? So what I can do is I can simply write the value of xi as xi1. Its value is basically 1 over here. Okay, and I can similarly write down the value of eta also. Okay, so eta, so this eta will be eta1 and its value is nothing but 0. Okay, so you can see in this particular here, so the eta value at node 1 is 0. Okay, so similarly you can go for y also. So if you use this, let us say this is your expression number 1. Okay, so if you rewrite this expression number 1, what you are going to get is something like a1, sorry, x1 equals to say a1. Okay, plus you will get something like a2 multiplied by 1, plus you are going to get this as 0. So let me call this as expression number 1 over here. Okay, so similarly we can write, let us say at node 2. So at node 2, the value of x will be x2, xi will be, so if you refer this particular figure, so the value of xi and eta at node 2 are 0 and 1 respectively. Okay, so here the value of xi is 0. Okay, so this will be xi2, and value of eta will be 1, and this will be eta2. So the same expression, that is expression number 1, so this can be now written as x2 equals to a1, okay, plus 0, plus now you have a3. So let us call this as expression number 2. So similarly you can write boundary condition, that is at node 3. So at node 3, definitely x will be x3 and xi will be xi3, its value will be 0, and eta will be eta3 and its value will be 0. So here you can see the value of xi and eta, they are 0 over here. Okay, so now with the help of this, now you can rewrite the expression 1. Okay, so expression 1 will be something like x3 equals to a1 plus 0 plus 0. Okay, so here this is nothing but your expression number 3. Okay, so in short what you are going to get is something like x3 is nothing but your x1. Okay, so this expression is now you have, that is x3 is nothing but your x1. Okay, sorry, a1. So we can use this value and we can rewrite expression 1, that is the small I. Okay, so if you rewrite this expression, so you can get x1 equals to a1. So a1 value is nothing but your x3 value, isn't it? Plus we have now a2. Am I right? Correct है बेटा ये?
Yes sir.
Okay, so this is nothing but your expression number 1. Okay, so with this expression number 1, you can get the value of a2. Okay, so a2 value is nothing but, now we have x1 minus x3. Okay, here we have already calculated the value of a1. A1 is nothing but your x3, isn't it? Now similarly you can rewrite the expression 2 also. So expression 2, what it says, x2 equals to a1. Okay, what is the value of a1? A1 value is nothing but your x3 plus a3. Okay, so now you can get the value of a3 from here as something like x2 minus x3, isn't it? बराबर ही है? Okay, so now we have started with the expression 1, where we have assumed x is nothing but a1 plus a2 times xi plus a3 times eta. So now we know the values of constants a1, a2 and a3. So I'm going to rewrite expression 1 over here. So earlier your expression 1 was something like this. So x was initially a1 plus a2 times xi plus a3 times eta. So now I can rewrite this term as a1. So a1 is nothing but your x3. Then we have a2. So a2 is nothing but x1 minus x3, okay, into xi, okay, plus a3. A3 is nothing but x2 minus x3 into eta. Okay, so now what we can do is we can rewrite all these terms so that we can get the shape functions. Okay, so let me expand this particular expression over here. So this x can be written as, let us say, x3 plus x1 times xi minus x3 into xi plus this is x2 into eta minus x3 into eta. Okay, so now I am going to take out the common terms of x1, x2 and x3. So I can write x equals to, let us take out x1. Okay, so if you see x1 over here, so x1 can be written as x1 into xi only. Okay, plus let me take out now x2. So if you see the x2 term, so x2 term is over here. Okay, and और कहाँ पर है तुम्हारा x2 term? There is no x2 term, isn't it? There is only one x2 term. So here I can say this is nothing but your eta. Then I can take out x3 term. So all the remaining terms are x3. So here we have 1, okay, minus we have here that is xi, okay, and minus here we have eta. Okay, so this is the expression in which now you can get the value of x in terms of x1, x2 and x3. So in short, what I can write over here, so x can be written as something like n1 x1 plus n2 x2 plus n3 and x3. Now here, what is the value of n1? So n1 value is nothing but xi, okay, your n2 value is nothing but your eta, and your n3 value is nothing but 1 minus xi minus eta. Okay, so these are nothing but your shape functions. Okay, I hope you have understood this. Yes, are there any queries, please? यहाँ तक समझ में आया बेटा?
Yes, sir.
Okay. Okay, so on the similar lines, we can also derive the expressions for the y also. Okay, so I'm just writing down the similar thing one more time over here. Only thing is here I have written y is nothing but a4, a5 and a6. Okay, so here you can have something like y will be nothing but your y1. Okay, xi will be at node, this will be xi1 equals to 1, and this will be eta1 will be 0. Okay, so you are going to end up with a similar kind of expression. Only thing is this will become now y1 equals to a1 plus, sorry, a4 will be there, this will be a5 and plus 0. Okay, and at node 2 y will be y2, this will be xi2, xi2 will be something like 0, and eta2 will be something like 1. So as a result of this, y2 can be written as something like a4 plus 0 plus a6. Okay, so let us call this as let us say uh, expression A. Okay, let us say this is expression B, and similarly at node 3 the value of y will be y3. Okay, value of xi will be xi3 and its value will be 0, and value of eta will be eta3, its value will be 0, and your original expression of y will become now y3 equals to, let us say, a4 plus 0 plus 0. Okay, so but if you solve this, if you apply the boundary conditions in the similar way over here, so what you are going to get is, so earlier this expression was y is equal to, let us say, a4 plus a5 times xi plus a6 times eta. So the same expression now can be obtained in form something like y will be this will be something like your x3. So here this will be y3 plus everything will be same. Only thing is x will be replaced by y over here. So this will be y3 into eta plus this will be y2 minus y3 into eta. So as a result of this, what you are going to get is the same expression, that is y equals to something like same, that is n1 y1 plus n2 y2 plus n3 and y3, where n1 n2 value, so these values they are exactly same over here. Okay, so n2 will be also same and your n3 will be also same over here. Okay, I hope this is okay with everyone. Okay, yes students, is it okay?
Yes sir.
Okay. So now for the time being, forget about this. Okay, so we have already calculated n1 n2 and n3. Now we can use a similar approach for u also, because you know that we have to establish a relationship between u and v with q. Okay, so for this purpose what I am going to do is something like u, I am assuming that u is nothing but a1 say q1 plus a2 sorry, my mistake. So I am assuming a relationship like a1 is equal to say this is a1, this will be let us say a2 into q plus a3, let us say this is q1 and this is let us say q2. Okay, so we can have a similar kind of approach wherein you can get the values of n1 n2 and n3 also, and as a result of this ultimately at the end what you are going to get is like this. So you can be written something like n1 q1 plus n2 q2 plus n3 and q3. Okay, and v also you will be getting something like v, that is n1, say now this will be q4 because this is the vertical deformation. Okay, this will be n2, this will be q5 and this will be n3 and this will be q6. Okay, so you can use the similar approach which we have seen over here. Okay, only thing is x and y will be replaced by now u and v, and here the local deformation here in place of x1 y1 now you have q1 and q4. That is the only thing. Okay, so accordingly now you can get the values of u and v also. Okay, is it okay with everybody now? Okay, everybody, do you want me to explain any of the portion one more time?
No sir.
Okay, so basically now we have a relationship between the u and v. Student, just a moment. Okay, fine students, will let me continue. So basically what we have done till now is the value of x. So x is nothing but the coordinates. So x is now depending on what? n1 n2 and n3. Okay, and your y is also now depending on n1 n2 and n3. Okay, similarly your v is also depending on n1 n2 and n3. V is also depending on n1 n2 and n3. Okay, now what are n1 n2 and n3? n1 n2 n3, they are the shape functions. Okay, these are what? Shape functions. Okay, and these n1 n2 n3 both they have the terms of either xi or eta or both. Okay, so in short, this component, that is x and y, now they are depending on xi and eta, and here also they are now depending on xi and eta. Okay, so why I'm concentrating on this, because at the end I need to find out the strain. Okay, and strain is generally calculated in terms of du by dx and dv by dy. Sorry. So now let us do some calculations over here. So if you want to calculate the strain, So strain. So strain is this is a 2D problem. So definitely you will be having a strain in x direction, strain in y direction, as well as the shear strain, isn't it? So for this purpose, let me write down. Let us say epsilon x, epsilon y, and gamma xy. Okay. Now what is epsilon x? Epsilon x is du by dx. Epsilon y is dv by dy. As far as shear strain is concerned, this will be du by dy plus dv by dx. Okay. So basically I need few things. Okay. Few things like I will be, if I want to calculate this, okay, I will be needing du by dx, as well as I'll be needing du by dy. Okay, so du by dx is required over here, and du by dy is required over here. I will be also needing, that is dv by dx, and I will be also needing dv by dy. Okay, here you see this is dv by dx and this is dv by dy. Okay, so my objective now over here is to find out what is du by dx, what is du by dy, what is dv by dx and dv by dy, because these are the terms which are required to generate the values of strain. Okay, so for the time being, let us focus on the first part, that is du by dx and du by dy. Okay, so let me write it down. So if I want to write du by dx, I cannot go for a derivation of du by dx. Why? Because u is not depending on x. Just now we have seen u is not depending on x, it is depending on xi and eta. So we cannot directly go for du by dx. Okay, so for this purpose, now what we have to do is we have to go for partial derivative. Okay, so I cannot go like du by dx, this is not possible. So in place of writing du by dx, I can write the same thing as del u by, say, del xi into del xi by del x plus del u by del eta. Okay, multiplied by, you can have del eta by del x. Okay, so can I write it like this, or am I doing anything wrong? बराबर है कि गलत है, बताओ. Yes students, am I right or wrong? Can I write it like this? अरे बोलो भाई. Yes, anyone? इसको ऐसा नहीं लिख सकते हैं because this is depending on two things. Okay, so what you have to do is we have to write it like this. Okay, you should write du by dz, because we cannot write du by dz. Du by dx हम लोग directly नहीं निकाल सकते हैं. ठीक है, so du by dx you cannot go for derivative, so we can go for derivative of du by dz. So this can be written something like, this is something like d u by dx multiplied by, this is dx by dz. Okay, and we can also write the same thing, this is du and this will be dz. Only thing is now you can have dy and dy over here, so that this dy and this dx is going to get cancelled. Okay, so on the similar line you can also write, this is du by dz. Okay, so du by dz now can be written as something like du over here, and sorry, du by d eta, and we can write the same thing, this is du by d eta, and here you can write dx, here you can write dy and dy. Okay, I hope this is clear to everybody. Shall I continue?
Required तो du by dx है ना?
हाँ, लेकिन du by dx हम लोग डायरेक्टली नहीं कैलकुलेट कर सकते हैं. So because of that purpose we have to go with this one, because now earlier case was different. Here the deformation in u direction is depending on x as well as y. दोनों चीज में उसका डिपेंडेंसी है. Because of that we are writing it like this. I hope this is clear to everybody now. ठीक है?
Yes sir. Sir, वो du by d eta है ना? del u
हाँ,
by del eta नहीं है ना?
this is du by d xi and du by d eta.
हाँ, और उसके सर उसके इक्वल टू के बाजू में सर पूरा डेल है.
हाँ,
यस सर.
ठीक है. So now what we can do is we can rewrite this entire term, because you see this is d del u by d xi and this is del u by d eta. So this I can write in the simplest form like this. Okay, so I can take out this du by dx and du by dy outside. So all I am going to get somewhere something like this. So this will be dx by say del x by say del xi, and this is del y by say del xi, and here you will be getting del x by del eta, and this is del y by del eta, and this now can be multiplied with something like del u by del x, and this will be del u by del y. Okay, so if you multiply these two matrices, you are going to get the same original matrix. Now here what is going to happen is this one. Okay, so this is nothing but your Jacobian matrix. Okay, remember in the 1D problem, your Jacobian matrix was of size 1 by 1 and it was dx by dz, but in this particular case your Jacobian matrix will be of size 2 by 2. Okay, so what we are interested in is du by dx and du by dy. हमको यही चाहिए, du by dx यहाँ पर चाहिए, du by dy यहाँ पर चाहिए. So if you want this, you have to just take a inverse of this Jacobian matrix, then and only you can get the value of du by dx. Okay, so here let me write down. कहाँ गया? Right. So let me write down over here. So this is du by dx, this is du by dy. Now this can be written as the inverse of this Jacobian matrix multiplied by, now you will have something like del u by del xi and del u by del eta. Okay, so now let us focus on each and every matrix. Okay, each and every element of this J matrix. Okay, so here this J matrix. Okay, so if I write this J matrix, so this will be J11, J12, say J22, sorry, J21 and J22. Okay, so let us focus on J11. So J11, if you see, it is del x by, so this is del x by del xi. Okay, now what is x? So x, we have seen that x is basically depending on your कहाँ गया? हाँ, so x is basically depending on xi and eta. So x is nothing but your we have also seen x is nothing but n1 x1 n2 x2 and n3 x3. Okay, so now we have to go for the same one. So we can have, this is del by del xi of the entire term, that is n1 x1 plus n2 x2 plus n3 and x3. Okay, now if you see the value of n1, okay, so n1 value, if you see, n1 value is nothing but your xi, n2 value is nothing but your eta, and n3 value is 1 minus xi minus eta. Okay, so we will be requiring it very frequently. So let me write it down over here. So your n1, okay, let me write down over here. So your n1 is nothing but your xi, your n2 is nothing but your eta, and n3 is 1 minus xi and minus eta. Okay, sorry, minus eta, not xi. Okay, so now if you go for this derivative, so you can simply say that is J11 now can be written as, so n1 का xi के साथ अगर तुम लोग derivative लोगे, so you are going to get x1. Okay, because n1 is value of xi, so ultimately you are going to get x1 only. N2 will be 0 because its derivative is with eta is there. N3 will be minus 1. Okay, so this will be minus x3. So your J11 term is nothing but x1 minus x3. यहाँ तक ठीक है बेटा, समझ में आया? Everybody, is it okay?
Yes sir.
Okay, so now similarly we can have something like J1 and 2. So J12 is dy by dxi. Okay, so this is dy by d xi. Okay, so this is d by d xi of, this will be now n1 y1 plus n2 y2 plus n3 and y3. Okay, so similarly you can get j12 on the similar form, because the value of n1 n2 n3, they will be going for derivative with xi only. So as a result of this, you are going to get something like y1 minus y3. I suppose this is okay. Okay, so on the similar lines we can have j21. So j21 is del x by del eta. So here you have d by d eta of, now you have n1 x1 plus n2 x2 plus n3 and x3, right? So now if you go for this, so now this time, first time you will be going for the derivation with eta term. So this is n1 will be 0 because it is not getting derived with eta. This will be 1, so this will be now x2, and this will be minus x3. Okay, so as a result of this, what you are going to get, this is x2 minus x3. And on the similar lines, j22 is nothing but something like dy by d eta. So this is d by d eta of, this will be n1 y1 plus n2 y2 plus n3 and y3. As a result of this j22, you will get something like y2 minus y3. Is it okay, everyone? Okay?
Yes, sir.
Okay. So let me focus on the J matrix now. So I am writing down J matrix over here. So this J matrix is now J11, J12. We have already calculated these values. So your J11 is x1 minus x3, J12 is y1 minus y3, J21 is something like x2 minus x3, and J22 is y2 minus y3. Okay, and ultimately what we are interested is in the inverse of this Jacobian matrix. Okay, so this inverse of this Jacobian matrix can be calculated as something like this. So inverse of this Jacobian matrix is the 1 upon determinant of J matrix. Okay, so determinant of J matrix multiplied by what is going to happen is this term will go over here. So this is y2 minus y3. So this term will go over here. Okay, then the 1 term will go at 2 terms. So this will be x1 minus x3, and this term they will remain same but with the negative sign. Okay, and this will be also negative sign, that is x2 minus x3. I hope I am doing it correctly. बराबर है?
Yes, sir.
ठीक है. And if you want to do the if you want to calculate the Jacobian matrix, so here the determinant of Jacobian matrix can be calculated by multiplying this minus this. Okay, so here it is something like x1 minus x3 into y2 minus y3 minus, we can have y1 minus y3 multiplied by x2 minus x3. And if you do this calculation with the help of values, what you are going to get is nothing but the twice the area of the triangle. Okay, so now here if you observe, our triangle is like this. Okay, it has got 1 unit length and it has got 1 unit height. Okay, so the rectangle area is nothing but your 1 by 1. So twice the area of the rectangle, twice the area of the triangle is nothing but your 1. So as a result of this, here 2a will be nothing but your 1. Okay, I hope this is clear to everybody. Okay? Yes, student, is it okay?
Yes, sir.
Okay. So now you see how we have started. We wanted to know what is du by dx. Okay, so for this purpose we need to have what is du by dx and du by dy. So everything now is written in this form. So out of which du by dx and du by dy is calculated as inverse of Jacobian matrix multiplied by this one. Okay, So we have already calculated this inverse of Jacobian matrix. Now let us calculate du by d xi and du by d eta. Okay, so I need to have du by d xi and du by d eta. Only this part is remaining, right? So du by d xi, this is remaining, and all is remaining is du by d eta. Okay, for this purpose we already know the value of u. So u is nothing but n1 u1, n2 u2, and n3 u3. So I'm just going for del by del psi of say n1 u1, or I won't say u1, this will be q1. Okay, n1 q1 plus n2 q2 plus n3 and q3, and here this will be du by d eta. So this will be d by d eta of n1 q1 plus n2 q2 plus n3 and q3. Okay, so we already know the value of n1, n2, and n3 over here. So n1 value, so this n1 value is nothing but xi, n2 value is nothing but eta, and n3 value is 1 minus xi minus eta. Here also let me write it down. So this value is xi, this value is eta, this value is 1 minus xi and minus eta. So if you go for its derivation, so this is du by d xi. So if you go for this, so this will be something like q1, this will be plus 0, okay, and this will be minus q3. बराबर है ये, ठीक है, and this is du by d eta. So similarly if you go for this, so this will be 0 plus q2 minus q3. I hope this is okay. ठीक है students, am I right?
Yes sir.
ठीक है. So what you are going to get over here is something like this now. So we have started with this. So I want to know what is my du by dx. Okay, so du by dx and du by dy, this is what I am getting at the end. So here this is du by dx and this is du by dy. Okay, this was the term, and now if you observe this, so here we have calculated du by dx and du by dy is nothing but the inverse of the Jacobian matrix. Okay, so let me write down the inverse of the Jacobian matrix. So inverse of the Jacobian matrix is like this, that is 1 upon determinant of j, okay, multiplied by let me slightly go up. So this is y2 minus y3. Okay, so this is y2 minus y3, and this will be minus of, this is say y1 minus y3. Okay, let me go. Sorry students, I got disconnected. Let me share the screen one more time. यहाँ तक हो गया था क्या? du by dx, du by dy, ये वाला पोर्शन? Yes, somebody please confirm. बेटा ये हो गया था?
नहीं सर, मैट्रिक्स फॉर्म कर रहे थे.
मैट्रिक्स फॉर्म हो गया, ठीक है. ये मैट्रिक्स समझ में आया कैसे आया? तो हेलो
सर, ये ऊपर वाले मैट्रिक्स है ना जो नीचे लाए?
हाँ हाँ, ये दिस इज लाइक we have calculated this du by dx du by dy as j inverse. So I have just written j inverse over here. Okay, and then it is multiplied with du by dxi and du by d eta. So we have already calculated du by dxi and du by eta. I have just written it over here. Okay,
Yes, sir.
यहाँ तक ठीक है?
Yes, sir.
ठीक है. Okay, so basically now what I'm going to do is I'm going to calculate du by dx individually, because du by dx is nothing but your epsilon x, isn't it? Du by dx is nothing but your epsilon x. So this can be calculated as 1 upon this can be calculated as du by dx. This is nothing but 1 upon determinant of j. Why it is getting disappearing, I don't know. Let me start fresh. I think there is some issue. Give me a moment. I think there is some issue with the software. Okay. Okay. Okay, everybody please pay attention now. So I'm just going for the multiplication. So this is du by dx, which is also called as epsilon x. So if you want, you can go for the row wise multiplication. So this is nothing but 1 upon determinant of j. Okay, multiplied by, now you will have a term something like y2 minus y3 into say q1 minus q3. Okay, then plus you have something like plus नहीं आएगा, ये minus term है. So let me write down minus over here. Okay, so this will be minus, so this will be y1 minus y3 multiplied by something like q2 minus q3. Is it okay? यहाँ तक ठीक है बेटा? Right? So now what you can do is you can isolate the terms of q1, q2 and q3 from this expression. Okay, so if you isolate these terms, so your epsilon x can be written as 1 upon determinant of j. Okay, multiplied by, if you take out this q1, q2, q3 terms, so what you are going to end up with something like y2 minus y3. Okay, then you can have y3 minus y1. Okay, and then you can have y1 minus y2. Okay, so one matrix multiplied by, now you can have q1, q2 and q3. Okay, so what I have done, I have just solved this. Okay, and I have just isolated the terms of q1, q2 and q3, so that now you can get the value of this one. Okay, so this is nothing but your b, a portion of a b matrix. Okay, so this portion of a b matrix is having q1, q2, q3, where q1, q2, q3, they are nothing but the nodal displacements at node 1, node 2 and node 3 in the horizontal direction. So here you see, this is q1 horizontal direction, q2 is horizontal direction, and q3 is your also horizontal direction one. Okay, so now on the similar lines, what you can have, you can also get the values of du by dy also. Okay, so जैसे हमने ये multiply किया है, so like we have multiplied by, we have done the multiplication of say this row and this column, so that we got du by dx. Okay, so on the similar lines you can also get what, du by dy. This du by dy can be required in the shear component. Okay, because if you remember, your shear strain xy is nothing but du by d, not dx, this is du by dy. Okay, plus we need to have dv by dx also. Okay, so in short, you can do the same thing for the y also. Okay, remember we have done everything. We have calculated something like we have, if you start from here, So we are interested in calculating epsilon x. Epsilon x is du by dx. Okay, so du by dx we cannot directly go for derivative, so that's why we are going for du by dxi and du by d eta. So on the similar lines you can write the same thing over here. Okay, on the similar lines here you can write something like dv by dxi and dv by d eta. Okay, so the same thing can also be done, and as a result of this you will end up with a similar matrix which is something like this. And finally what you can get is your B matrix. So your B matrix will be having the three components, that is du by dx, dv by dy, and du by dy plus dv by dx, which is written over here. Okay, so this can be written in a very simplified form at the end, which is like this. So we can have say your strain. Okay, so strain can be epsilon x, epsilon y, and gamma xy. Okay, so this can be written in a simplified form as this is nothing but y2 minus y3. This will be 0, this will be 0, this will be x3 minus x2, this will be also x3 minus x2, this will be y2 minus y3. Okay, I am putting a dotted line over here. This will be y3 minus y2, this will be 0, this will be 0, this will be x1 minus x3, this will be also x1 minus x3, this will be y3 minus y2. Okay, again there will be a dotted line, and lastly we have y1 minus y2 with 0, this will be 0, this will be x2 minus x1, this will be x2 minus x1, this will be y1 minus y2. Okay, multiplied by, now you will be having something like this is q1, q2, and q3, because these are the horizontal components, and the vertical components will be q4, this will be q5, and this will be q6. Okay, so let me write down properly. Okay, so this will be like this. Okay, so now if you multiply, let us say if you multiply this row with this column, so y2 minus y3 multiplied by q1, so you are going to get this epsilon x term over here. Okay, so in this way you have to go for a derivation of this matrix. And if you see this is very much similar to your B matrix. This is nothing but your strain displacement matrix. So this is strain, and this side we have displacement. Okay, so this is how the strain displacement matrix comes into picture. And if you refer the notes of your Cartesian coordinate system, this was something like b1 c1, isn't it? तो तुम्हारा ये क्या था, b1 0, b2 0, b3 0, then this is 0 c1, 0 c2, 0 c3, this will be c1 b1, c2 b2, and this will be c3 and b3. याद है ये? Okay, so these are the same values. Okay, only thing is you have a term which is coming out over here, that is the determinant of j. I think I have missed over here, so this is nothing but the determinant of j over here. Okay, so once these values are known, you can generate the k matrix. Okay, so this k matrix is nothing but integration over the volume, then we have b transpose into d into b over dv. So now this b is constant term, so b transpose can be taken out. Okay, d is also a constant sum, this b is also a constant term, so this can be integrated over volume into dv. Okay, so now this dv can be let me write down over here. So this is integration over the volume, this is dv. So this can be written in a very simplified form as integrated over the area. So we can have thickness into d area. Okay, now here the dA is spread in the x and y direction, but we are talking about the artificial the natural coordinate system. So this dA can be written as -1 2 plus 1, again -1 2 plus 1, so thickness will come out. Okay, and dA now can be written as this is d xi and d eta. Okay, so this is how you have to go for the derivation over here. Okay, I hope this is understood to everybody. And if you go for the integration, so ultimately this thickness will come out, this Jacobian matrix will come out, and this integration part is now going to give you the area. Okay, and this area of one triangle is half, because if you see the if you see this particular triangle, so on this side we have length of 1 unit, and on the top we have the length of 1 unit. So the area of this triangle is nothing but your half. So as a result of this, you will be getting a K matrix, that is the stiffness matrix. K elemental matrix will be, this will be B transpose into D into B. So this will be a constant term, multiplied by, you will be having a thickness, multiplied by, we will be having a Jacobian matrix divided by 2. So this is a similar matrix which you will be getting using the Cartesian coordinate system also. Okay, I hope this is understood to everybody. ठीक है? Yes students, are there any queries? ठीक है?
सर
Yes.
जब सर हम ये dA के साथ इंटीग्रेट करेंगे तो सर d eta इंटू ये d xi इंटू d xi ही आएगा क्या 2 बार?
सॉरी, मुझे नहीं समझ में आया क्या पूछ रहे हो
सर ये जो सर
इंटीग्रेशन बोल रहे हो ना तुम?
हाँ इंटीग्रेशन सर.
See, we are going for integration of area. So here if you see this particular term, ये दिख रहा है?
Yes sir.
हाँ, इसमें अगर तुम देखो, इसमें t अगर तुम बाहर निकालोगे, so इंटीग्रेशन ओवर द एरिया इनटू dA, तो तुमको क्या मिलना चाहिए? एरिया मिलना चाहिए सीधा सीधा.
Yes sir.
बराबर है. तो एरिया जो है उसका ट्राइंगल का एरिया है, दैट इज नथिंग बट हाफ. उसको मैथमेटिकली वी आर रिप्रेजेंटिंग इट फ्रॉम, सॉरी आई थिंक आई हैव रिटन रॉन्गली ओवर हियर. दिस शुड नॉट बी -1 to +1, दिस शुड बी 0 to +1. Okay, this should be 0 to +1 because your element is from 0 to 1. ठीक है? तो ultimately your dA is nothing but the area of the triangle, and your area of the triangle is nothing but half in the natural coordinate system. I hope this is clear. ठीक है?
Yes sir.
ठीक है. So next class probably we will take one simple example of this. Okay. So we will meet in next class. So let me stop the recording, and I think everybody can leave the meet now. If you have any queries.